Okay, thank you. So I was charged today to talk about magnetic stratigraphy a little bit, and I lost my title. Well, we'll see how much other things I lose up there, but we're going to talk about how the geomagnetic field and its variability can be used to help us understand time. All right, there's a large list of collaborators and acknowledgments, and I just sort of wanted to list a lot of the folks who I've been working with. None of these, they can't be held at fault for any of the things I say. Of course, NSF is here on the bottom, and that all fit on my screen, but it doesn't seem to fit here. But we always need to welcome and thank the funding agencies. Okay. What is magnetic stratigraphy? That's what that's supposed to say. Well, basically, it can be broken into two specific parts. Environmental magnetism, which I'm not going to talk about very much, but that would be things like magnetic susceptibility that we all measure, measuring lithologic variability. And here's an example from some work that Catherine Cassell did of how the magnetic susceptibility record in the North Atlantic compares with the Greenland ice core oxygen isotope record, and that could be used as a stratigraphic template and has been used. What I'll focus on more is the geomagnetic aspects of this, and this can be broken into two parts here. The Paleomagnetic record and really the cosmogenic nuclide record, because the production of cosmogenic nuclides is going to be a function of geomagnetic field strength and its orientation and morphology. So how those variations are going to affect the Paleomagnetic record. As examples, we give the Paleointensity record here, and then an example of cosmogenic nuclide flux. We're looking at the beryllium-10 and ice cores both in the southern hemisphere and in the northern hemisphere, and this large anomaly associated with the low and paleointensity that's associated with the Lechamp excursion. The relationship between geomagnetic intensity and cosmogenic isotope production is really not completely constrained. We don't know all the dynamics of this yet. So as we say, really there's a lot to be resolved in looking at the intercorrelation of the two. Mostly what I'm going to focus on for most of this talk is how the geomagnetic field itself varies and the impacts and the stratigraphic uses we can get of this. Of course, this picture is, of course, not to scale, but just showing two of the major players within cosmogenic nuclide production, both the geomagnetic field over here and the sun's magnetic field as generated over here. And together these work to really control the production of those isotopes. Okay. Easier to read over here. Make this a little easier. Okay, paleomagnetic stratigraphy, which we're going to focus on, is really the use of geomagnetic change as measured in sediments or rocks or other geological materials and archaeological materials as a stratigraphic marker. And this comes in kind of four flavors: reversals, excursions, polarity intensity, and paleomagnetic secular variation. And I figured I'd sort of run through, because this is a broad audience, as sort of examples of each of these and where we are presently in the basic state of the art. Okay, so the geomagnetic polarity timescale, cut off at top here, is kind of shown here with an example of the black equaling normal polarity and the white intervals equal reverse polarity going through the Cenozoic. These are actually cord sediments from the North Atlantic, and basically what you would do is measure these shipboard. You'd get the interpretation of normal polarity, reverse polarity, normal polarity, and you would see, you could make an interpretation of that over here in this black and white diagram, and then you would correlate it to the basic time scale of the geomagnetic polarity time scale, thus generating time. Geomagnetic polarity time scale is applicable to many different geological materials. It's globally synchronous at a sort of geological time scale and environmentally independent. That's one of the big points. It's relatively geologically fast. Reversals take approximately 5,000 years, not necessarily paleoclimatologically fast. Polarity zones provide distinct fingerprints. Correlations only provide reversal boundaries. I think the key thing with it is it can be measured in a range of materials. You can measure it in ocean sediments. You can measure it in lake sediments. You can measure it in rocks. You can get measurements from archaeological materials in the near term. So it's widely applicable. But if we look at it in detail, and if you look at magnetic reversals in detail, and here's a few versions of the upper and lower Jaramillo shown here in terms of VGPs, their intensity records below it, and the oxygen isotopes, and how that would look in detail, you find that it takes time for a reversal to take place. So these aren't exactly instantaneous phenomena. They have significant duration associated with them. If you look at a map space, you find that, for example, in the upper Jaramillo, you find these are 4 different versions of that. They all show a common sort of feature initially before the actual reversal takes place. So you have this excursion before you have a reversal. So there are dynamics associated with that, and it actually does give us a unique opportunity that you could use these as high-resolution stratigraphic tools potentially within a reversal interval. It's not something that's really been done, but it's something that potentially could be done to look at very interesting isotopic stages in detail by sort of looking at these dynamics and trying to compare this in other places. The scale of this variability in terms of spatially is hard to know at present because it's not been measured in detail outside of the North Atlantic, but I think a lot of the potential is there, and some of these features should have very large scale dynamics, so it could provide very tight time control in the more distant past. If we move on again and talk about excursions, what's cut off here is the idea of the geomagnetic instability times scale, which is something that Brad Singer has been sort of pushing along and pioneering. And it's the idea that magnetic excursions, which is a list of some of the diagnostics of a magnetic excursion, but these are features in the record. They're short-term reversals that occur throughout history, and we're now finding that they're common features of the geomagnetic record. Here's an example of them as recovered in sort of the Bermuda Rise ODP drilling, that these features are very common in both declination and inclination. They occur in lows in intensity. This is an intensity plot over here, and you find these things really associated with most lows in intensity in this high accumulation rate record. They are also found in lavas, and what Brad has been working on is the argon-argon dating of a lot of these in the lavas and trying to correlate them into the marine record so that we have sort of precise stratigraphic markers. The difficulty with a lot of these things is they really are non-unique. You don't know one from another particularly, so it can be difficult to work with. So if you compare these with their sort of intensity profile, you have sort of a more fruitful way of really coming up with a time scale. Move along, we'll look at paleointensity. Paleointensity is sort of one of the newer splashes, and it's really showing that we can provide sort of chronostratigraphic framework during times of constant polarity. Here we are showing 3 different stacks going back several million years, including the most recent that Jim Channel put together based on all these particular cores. This one is sort of unique, is it's directly tied to the oxygen isotope record, and therefore it's a complementary stratigraphic approach that's been widely measured and really in all these different cores, primarily located in the Western Pacific and the North Atlantic, with a little bit in the South Atlantic here. And this shows the oxygen isotope records from that stack compared with the Lezecki, and that's where the time scale, the Lezecki and Ramo stack, and that's where the time scale comes from, and the paleointensity record, with the red record being this higher resolution piso stack compared with the blue being the lower resolution from Valet et al. Scent stack here. So you can see that they're fairly similar, but the time scale varies a bit, and we've increased the resolution. This has been now pushed back 1.5 million years and provides a complementary stratigraphic record. The real test on this will be sort of taking this and applying it into terrestrial settings and attempting to use it there to sort of bring the dynamics, the climatic dynamics in those environments back into the marine realm and sort of compare how the processes are working. This stack below only goes back 80,000 years, and it's just a comparison between the Piso stack, which is in black here, and the Glopus, Carlo Lagge's 85,000 year stack, sort of high resolution stack going this time period. And I think they compare quite well in general, showing that the longer term stack, even though it's based on lower resolution records, captures a fair bit of the variability in terms of what should be the global variability in the record. So I think we're making a lot of progress on paleointensity, and it's going a long way. So and this just shows again some more of the paleointensity and the fact that a lot of the excursions are often found associated with these lows in intensity in the record. Okay, finally, directional secular variation or paleomagnetic secular variation, widely applicable and used in Holocene timescales as paleointensity can be. And this is just showing the Fish Lake record of inclination here, which is the deviation in the vertical plane from horizontal, and declination, which is the deviation from in the horizontal plane from essentially geographic north. And as you can see, over the last 10,000 years, there's been substantial variability, and some of this variability is quite abrupt in its nature. And we're finding out from higher resolution records, and as we'll talk about, that many of these features may represent some significant reorganizations of the field and be rather abrupt and provide some really tight chronostratigraphic tools. One of the more interesting aspects is trying to understand the dynamics of what this means. Is really a newer suggestion is that these things may be driven by essentially dipole wobble rather than local variability, and therefore there may be some global synchronicity of this by running a circuit through where the pole might be. So a sort of simple test of this, and this is basically showing well, here's the north magnetic pole, here's the north geomagnetic pole, sort of the best fitting dipole to that. Here's the geomagnetic equator on this compared with that. So you can see everything sort of nearsighted over here towards North America. And to make a simple test, we've compared, for example, here, reverse declinations in Iceland in red from a record that I've been working on for a while, and lava-derived data from essentially the Cascades in the western U.S., the inclination data. So when you're over here, basically your inverse declination, if it's a dipole, should look like inclination over here in the western U.S. And that's essentially what we see within chronological uncertainty. We've adjusted actually this chronology a little bit, which does move it a little bit forward based on some tephra correlations. And we're starting to see that really a simple dipole might predict a lot of secular variation. Okay, so the question is, you know, where do we go from here? This is sort of where we are in terms of magnetic stratigraphy. We have these sort of 4 different types of things we can use, and how do we improve upon this? How do we go further? How do we make better use of this? And basically, what we need to do is really derive a better understanding of the geomagnetic field and the magnetic recording process. We should be able to improve magnetic stratigraphy. The essential problems come about is that there really is no theory of geomagnetic change. This idea that dipole wobble might control secular variation is one step towards that, but in general, we don't have a theory of geomagnetic change. We know that the magnetic field is driven by magnetodynamics within Earth's core, but we don't know what causes the change. But I think we have some hints now that there is hope to actually put together a theory of geomagnetic change. Our understanding of the magnetic acquisition process in sediments is far from complete, and we could do a lot more towards understanding that. and in the rest of the talk I'm going to point out some ways I think we can go further in that. And you know, more practically, why it works in some places and why it doesn't work in others is always been an enigma. We're starting to get some ideas on that. We have some places we think it works better than others, but we do need to know work. So we can say, you know, is this going to be a tool that should be used in this area or not? You know, where does it work and where doesn't it work? And that's an important question. So towards developing a theory of geomagnetic change, one of the most important aspects towards that is really the idea that's cut off at top, but does the mantle itself and the really temperature distribution of the lower mantle control the dynamics of the geomagnetic field? Is that really controlling the convective structure and providing sort of a boundary condition framework similar to the way continents provide a boundary condition framework for climate that may control the dynamics of the field? And what's shown here is basically temperature distribution of the lower mantle, and then that's used to control the output of a geodynamo model from Dave Govens, and this is work of Dave Govens's. And here are magnetic flux that you get based on this temperature distribution and placed on this geodynamo model. And you find that the core gets locked to the mantle, and you get positive flux in this area and flux over here with these two symmetric features in the southern hemisphere. And this is what you see in the actual data. It's more complex, but you see similar, really these flux lobes are very similar features. So it's suggesting that we may actually be able to come up with a dynamic player or structure on the geomagnetic field that may allow us to assess why and how it changes, and maybe even put some timescales on these processes. So if we are to move forward in this, where do we go? Well, one of the things I think we can do to really do this is put a coherent focus on really the last intensity cycle, which I would suggest is basically the last 50,000 years from the high pre-Lechamp through the Lechamp low, going through this complexity period into basically the Holocene high. And this is an attractive period because we can basically independently date it, so we can compare it in a regional aspects. We can it captures almost all types of geomagnetic variability. We don't have a reversal, but we have an excursion in that interval. So we capture both high intensity and low intensity, a lot of variations. It's not buried too deeply, so we're basically able to collect records at high resolutions, which you can't do when you sort of work your way back to, you know, the Bruns-Matayama boundary. If you're going to look at a high resolution record of that, it's 780,000 years ago, and it might be 100 meters or 200 meters deep. So it starts to get to be hard to resolve high resolution records. Over the last 50,000 years, we can do it. We also need to work to extend the historical record. And this particular feature, I don't think you can see, but this is North America under this flux lobe, and this is Siberia. The North Atlantic is in between. Here's Greenland. There's also this other feature in the Holocene. And this is the persistent structure of the field that you get if you average it out over the last 400 years. Is this structure something that holds in the past, and can we work to test whether this provides a background framework on the paleomagnetic record? If we can do that, then we should be able to really start to develop this theory of geomagnetic change. And then we need to make a concerted effort. We need to understand how the geomagnetic field and the cosmogenic nuclide record really relate, and that's kind of shown here. It's the Olivier Marchal C14 production record with some higher resolution paleointensity records from the North Atlantic here, 1305, a European archaeomagnetic record, a Scandinavian stack, some high Arctic records from two different lakes up in Ellesmere Island, what is thought to be the global stack from a model, and also some archaeomagnetic results. And they all show a lot of similar dynamics. The question is, how much of this variability is driven by geomagnetic change versus solar change? And that is something we need to establish, and stratigraphically that's important because this is a very well dated archive. If we can tie ourselves and place ourselves into that, then we have a really tightly constrained stratigraphic tool. And finally, we need to make concerted efforts to really get high quality data. And I like to show this picture of Ron Grout because in the middle here is a non-magnetic core barrel that was used by IODP, and it makes a significant difference in the quality of the magnetic records that you get when you compare it with what you have using a regular sort of steel core barrel. It actually makes a significant difference and really reduces the magnetic overprinting problem that's often plagued a lot of ODP and IODP legs. So using technology and making the concerted effort, we can improve sort of the results we're getting. Okay. So I figured with the rest of my time here, I'd show a little bit of some studies that we're doing to work on these problems. And basically the question here is, does the paleomagnetic record that we measure, the paleomagnetic output here, looking at a U-channel sample measured on a small axis cryogenic magnetometer, how well does that approximate the geomagnetic input, what's driven? So when we work through that sediment transfer function, how good a job does it do? And I think that really depends on where you go. But one example here, this is the last 80,000 years, and you see the blue curve is the low resolution scent stack compared to the black curve, which is the higher resolution GLOPIS paleointensity stack. And you can see there's a lot more amplitude captured in that particular stack, so that we are missing information when we do look at lower resolution records. Okay. So let's see, what's that? The problem, basically sediments act as a low-pass filter, so we're missing information within it. And this is just a sort of schematic of magnetic particles falling through the water column, getting deposited, going through bioturbation, eventually locking into the magnetic field here applied towards it. The question is, you know, how much is lost going through this particular filter of sedimentation and different sedimentation rates? How much is the offset in terms of the lock-in depth, this depth here, what's called the post-depositional remnant magnetization that Ted Irving sort of started talking about in the 60s. How much of effect did this really have? What is the offset in the paleomagnetic record, and how does it affect our data? Here's another model that Johan Giotto put together in a paper with Channel and Giotto, just looking at a sigmoidal function, looking at the mix zone as having no magnetization, and then it being progressively locked in at some depth below, which they used a lock-in depth at which 50% of the magnetization is acquired. And they came out with depths of about 15 centimeters or so of lock-in. But it really depends on what sort of sediments you work on. So the actual observations of this are very few, and most of them are based around the Bruns-Matayama boundary, which is a long time ago. Okay. So to do this, you need a high-resolution record, and in Iceland here, we have developed that. The red record is a record from MD99-2269, about 25 meters of Holocene. It has more than 44 dates between two different records and a bunch of tephra layers that help constrain the chronology. This is the inclination, declination, and the blue is the predicted declinant ink for that site based on some model results, which really show that we think we have a really strong record here, that the model results aren't able to capture some of the dynamics there. What we need is a deep sea sediment record to really understand this typical sort of IODP sort of record, and site 1305 sort of gave us this off the Eric Drift here in the North Atlantic, and these are shipboard results showing very repeatable inclinations and declination data that strongly mimic what we had in Iceland. If we compare the Iceland data, it has a very strong chronology, and this just shows the chronology. We've stacked two different declination and inclination sets here from this record in East Greenland and this record in North Iceland. You can see the C14 dates stacked very nicely in depth, and we've added all these tephra layers. We've used the terrestrial tephra ages to sort of help us with any sort of radiocarbon reservoir effects, and we've developed this record below, showed below. And the blue record, this is just showing these global continuous field models, which is going to be a very important technique in the future. sort of needed to mention that Monica Corte has been working on a lot, and those are going to be very important. Just another record we have from the St. Lawrence estuary, it too is well dated. And if we get to the, well, I'll skip over that one because I'm running short of time, but that was sort of developing the chronology for 1305. But if we look at the data, this is our deep sea record from 1305 in the center. In declination, you can see some of these abrupt changes in how large they actually are in the Icelandic record. And you can see the chronological offset that you have in declination between our record in the St. Lawrence estuary here and our record from Iceland over here, and the offset that we have in declination, similar offset and inclination, and you can come up with a pleasing fit to both records, showing the best fit to either, using basically the same thing. This allows us to compare the age model here above with the age of the magnetization below, and this is the offset that you get. It's variable through time. It basically gives us an average of about 450 years offset with a depth offset of 25 to 30 centimeters. That's a bit of an overestimate, I think, because we haven't taken into account reservoir corrections in the North Atlantic into the data from the age of the sediment. But it's something that's in the ballpark, and it's also something I think that's really not continuous because we don't really see that sort of large-scale offset when we look at lower down in the record. So it really depends on the type of sediment, but it's something we're understanding and something we can hopefully correct for. Okay, one more thing. We should show that the sediment records basically recover very similar sort of records, and this is the VGP profile, and I wanted to bring this out, is this sort of spaghetti diagram are the plots of where the pole would be in the North Atlantic during the last 8,000 years. And what you see compared to the structure of the geomagnetic field, this has sort of been scaled, the smaller one. You can see that basically the movement of the pole fits within these sort of features. So it looks like these dynamic sort of features that appear to be controlled by the mantle dynamics on the core are likely controlling the secular variation that we see. And this large scale feature at 2,500, about 500 years BC, kind of interesting, has been associated with sort of sightings of the aurora in biblical locations. So the geomagnetic record is well matched. The time is offset a little bit. So where do we go? Well, we're working on this in more detail now. And this is just showing a bunch of records that we've now obtained from the North Atlantic that we're starting to work on with their own C14 dates and how they compare with our geomagnetic template, showing that there is a bit of a lock-in depth effect, and we're going to sort of model this. We now have enough observations that we should be able to provide a bunch of constraints on this and really get at how sedimentation rate plays a role in this. Is it consistent, and what's going on? And finally, this is the 1305 core top, and I just wanted to show this diagenetic change that starts to happen at about 15 to 20 centimeters, finally going about 25 centimeters. It does affect the magnetic properties, which are shown in blue, and it brings to a point that's not shown here, but how does diagenesis really affect the paleomagnetic lock-in, which is another feature we haven't worked on, but something we'll have to look at. So I think my time is up, and I'll leave it there. Thank you.